All right. We're going to now look at the electrostatics relationships using calculus. So just as a review, when we did this with algebra, we looked at these four quantities. So there's force, which is a vector. Of course, a force is that interaction between two particles. Then we had the E field, which is a vector. We had the sources and sinks rule. It just states the direction of force a positive charge would feel at that location. We can also think of it as the force per unit charge. We have electric potential energy. And again, energy, and especially potential energy, is shared between two objects. So that's a scalar. And then we have electric potential, and that is our energy per unit charge. We thought of it as a sort of electric height. And we can translate between the 1 and 2 charge versions just by multiplying or dividing by a test charge Q. So again, we can quickly turn a field into a force acting on a specific particle because that field is global. But if we want a specific local force, we can just attach a Q to the field. Same thing with our energy change. If we want to see how a specific particle would change its energy in that global potential, we just tack on a Q there. But our remaining relationships, which we've approximated using algebra, is we can use mechanics that states that force is the negative of the derivative of potential energy. And we can use that to recover our formal forms of the force and field relationships. So we can create a field potential relationship to say that the E field in a certain direction is the rate at which the potential is changing in the downhill direction. And then we can find a potential difference by actually integrating that electric field across a certain path. And we'll actually rewrite this. Instead of using dot products, we'll often visualize this instead as the parallel components of the E field being integrated. Because if you add up all of those downhill contributions, you're going to get the total amount you've traveled downhill. Because again, E points down towards these lower electric potentials. So if we sum up all of our downhill contributions, all of our slopes, we should get our net change. So here we have our big electrostatics flowchart fully complete. So we see that we have our force, our field, our potential energy, and our potential. These are just our definitions, how we translate between the 1 and 2 charge versions. And then by applying these mechanics relationships to the single charge version, we create our field potential relationships. So that's going to be our first task, is to prove this bottom part of the flowchart. So we want to verify our two relationships down here. So first of all, it is a given. Our starting point here is that force is the negative of the derivative of potential energy. And that gives us the force in a specific direction, let's say the x direction. So now what we can do is, of course, we can just divide out a q. So we can just divide out a q from both sides. And now if we use the fact that electric field is defined as the force per unit charge, we can write this as the electric field in the x direction. And then we can move this derivative out in front because the derivative is what we call a linear operator, meaning it doesn't matter if you multiply then take a derivative, if this is a constant, which it is. If it's not a constant, of course, you have to use the product rule, but we can just rewrite this as the negative derivative of u divided by q. And in the same way that field is force per unit charge, potential is potential energy per unit charge. So we get that the electric field is just the negative derivative of the potential. Because we also know that V is defined as U divided by Q. And now we can get the other relationship as well just by integrating this. So if we start from the fact that negative dv dx equals EX. We can multiply both sides by a negative dx to get dV equals negative EX dx. And now we can integrate both sides to get all of the contributions. And we can see that if I integrate all of my tiny changes in potential, that gets me my total potential change. And then I get a negative outside the integral. And we see that this EX dx takes care of that dot product or parallel part. So that gets both of those relationships. All right, so now that we have talked about this definition, we're going to start with going to electric field if we're given the potential originally. So this came about from graphing electric potential, and we looked at these equipotential lines and showed that the E field is always going to point downhill. So we use this to kind of approximate the field strength at different locations if we were given an equipotential diagram. We looked at that spacing between the lines, and if the spacing was less, it means you lost more height in less space, so it was steeper, so your E field was greater. And that, in the language of derivatives, is why we get the E field in a certain direction is just that downhill slope. I should also note that there is a multivariable calculus version of this, where if you wanted the total field and if you had all these different coordinates, maybe if we just did like the XY plane to start, we can actually write the electric field as the negative of a multivariable calculus operator called the gradient, which is given this upside down delta symbol called nabla, that operates on our potential. And what that means is that instead of just having one derivative, because instead of just operating in 1D, you could have a rate of change in the x direction and a change in the y direction. So we actually have these two derivatives. And if you just wanted a component, you just take a part of it. And anytime there's multiple variables, we just put this little curly d on the derivative operator just to show us that multiple things are changing. So for a really quick symbolic example of this, the electric potential on the x-axis, we have a function that's given, and we have a positive constant. So if we try to graph this, we see that it's an even function with a positive coefficient. So it's just going to be something parabola-ish. And just kind of looking at the behavior of this, we know that positive charges accelerate downhill. So we know that a positive charge is going to get sucked into the center of this bowl. Negative charges would get pushed out of it. So we want the E field. We know that the E field is given as this downhill slope of the potential function. And our potential function is just ax to the fourth. So we're just taking the negative of this derivative. So it's just a basic power rule here. That's just going to be 4 times ax cubed. And of course, this is a vector. So since we're dealing with an x field, I'll attach an I hat vector to that. Notice this does make sense because this tells us if I place a charge somewhere over here that's positive along the positive x-axis, it is getting pushed left towards the center of that bowl. Now, if we do the electric force on an electron placed at a certain position along the positive x-axis, we know that we can get to force just by multiplying that charge into the field. And in this case, an electron is an elementary charge with a 1 unit of negative charge, and our E field was given as negative 4ax cubed times I hat, or to the, or left, 4ax cubed left. But again, we deal with the unit vector notation because we can easily see what's going to happen with the sign changes here. So the negatives cancel, so we get 4ax cubed times E, and then positive I hat. And this x is x0. So notice this makes sense because an electron, if it's placed in this potential, is going to accelerate to the right if it's on the positive x-axis, because the negatives go towards higher potentials, or the opposite of what positives would do. Now we have a numeric example. So the electric potential in kilovolts, so this is thousands of volts, along the y-axis is given by this function, where y is measured in meters, so we got a cubic here. There's exactly 1 point along the x-axis where a charge can be placed and experience no net electrostatic force. So if it's experiencing no force, we know that there must be no field, because we know that if there's no electric force, we know that QE equals 0, so that means that the electric field has to be equal 0. So all we want to do is figure out where this electric field is equal to 0. And if the entire field is 0, well, of course it means the y component is going to be 0. So we're going to use the fact that the y component of the electric field can be found by taking a derivative, that sort of downhill slope idea. So we just take a y derivative of our original function, 2y cubed plus 6y squared plus 6y. So now we can just do some basic power rule things with that and set it equal to 0, because we know that if there is no slope or no downhill pointing, there's going to be no direction of force. So we know that 0 is going to be equal to the negative of, bring the power down, 2 times 3 is 6y squared, bring the 2 down, 12y, and take away y gets us to 6. And this is actually not bad to solve. Like, don't think you got to use the quadratic formula on this, because this is actually factorable. Because everybody has a 6 in it after I cancel that negative out, because that's not going to make something 0 or not. I can factor out a 6, and I can get y squared plus 2y plus 1 is equal to 0. And this factors. So you could use your perfect square identity, or you could say, what two numbers multiply to 1 and add to 1? Or sorry, and add to 2. Well, that's going to be 1 and 1. So 6 times y plus 1 times y plus 1 is equal to 0. And solving this gives us a unique solution at y equals negative 1. And I did also ask, how could you find this if we gave you a graph? Well, if we gave you a graph, you're just going to look for that point on this cubic where there's no slope. And in this case, it would be this plateau right here where there's a flat tangent line. So let's calculate the electric potential at y equals y0. We're calling this y0. So V of y0 is just going to be the potential when y is equal to negative 1 meters. So our original potential function was 2 times y cubed plus 6 times y squared plus 6 times y. So we get negative 2 plus 6 minus 2. And that's just, or sorry, minus 6. And that's just going to be minus 2 kilovolts. And because we might want it in just regular volts when doing some math later, this is going to be negative 2,000 volts. And now, of course, we're dealing with potential, so you know there has to be an energy problem in here. A positive point particle with mass and charge is placed at the origin, released from rest. Calculate the speed of the particle as it passes through y equals y0. So first of all, we know that the potential at 0 is going to be 0, because if I plug in 0 to the potential function, it's there. And we know that positive charges are going to accelerate towards lower potentials, so it makes sense that it's going to go towards this negative 2,000 volt place by its own, on its own here. So we're given, well, we know that v of 0 is going to be 0, because if I plug into the function, there's just a bunch of y's everywhere, so that goes to 0. And v of y0, we said, was negative 2,000 volts. So anytime we deal with potential, we usually like this relationship that change in kinetic energy is the opposite of change in potential, which can be written as Q times delta V. So now we can do this because we know that our Q that was given was 5 microcoulombs. So micro is 10 to the minus 6. And delta V, well, delta V, I started at 0 and I went down to 2,000 volts. So 2,000, and that's going to be negative, which makes sense because I get a negative and another negative. So my change in kinetic energy is actually going to be positive 0.01 joules. And then we just use the fact that delta K is equal to 1/2 mv squared at the end minus 1/2 mv squared at the start. We are given this particle starts from rest, so we know that there's no initial kinetic energy. So our final velocity is just the square root of 2 times delta K divided by m. And all of those things are known to us. And working this out actually works out perfectly nicely to a whole number of 0.4 meters per second. Or not a whole number, but you know what I mean, not irrational. So that's our final speed. All right, now we have a graph to interpret. Here's a graph of potential along the x-axis. And we want to begin by ranking the magnitude of the field at each of the points from least to greatest. So anytime you have a graph, think about how what you're asked about relates to the graph. And usually there's 3 options. It's either the graph, it's related to the slope of the graph, or it's related to the area. And in this case, we know our relationship is E is what we're ranking. And this is an x. So E in the x direction is equal to the negative downhill slope of the potential. So this is the negative of the slope. And since we're just looking at the magnitude of the electric field at each of these points, we're just really looking for, we know that the magnitude of the electric field is going to be the absolute value of the slope. So let's do that in each of these cases. So first of all, at B and D, we see that this slope is completely flat. So we know that dead last is going to be B and D. Because B and D, there is no downhill. So a positive charge will experience no force at that spot because there's no downhill for it to get pushed at those specific points. Now let's look at A and C. Well, we can just do some basic rise over run things with A and C because they're straight lines. So A goes up 1, 2, 3, right 2. And C goes down 3, right 1. So notice that even though C is negative, it's still a steeper slope because I got 3 over 2 versus 3 over 1. So C is actually my steepest slope. Oh, I don't know why I wrote 3 there. C. So we're just ranking the slope. So here we have the slope is equal to 0. Here we have the slope is 3 over 2. And here we have the slope is 3 over 1 in absolute value. So again, we're just ranking the slopes here. And if you have these nice geometric graphs, chances are it's going to be a slope or area problem or both. AP Calc likes these a lot. All right, now we have a bit of a spicy problem that I'd say, because we don't have one variable, we have two. So here's where we bring up that gradient idea. So the electric potential in the xy plane, so we're not just restricting ourselves to an axis anymore. We have the xy plane is given by v of x comma y is equal to x squared plus 4x, or sorry, plus 4y squared. So this potential is going to be strictly positive, and if we imagine what this looks like in 3D, we have v equals 0 at the origin, so maybe let's just say that, because I'm sure that will be helpful for later. And everywhere else, v is positive, because I'm just adding squared quantities. So we know that our lowest potential is at the origin. So first we want to describe the shape of the equipotentials, which means what are these curves that this function is constant on. So the easiest way to do this is definitely just to plug this into Desmos and kind of like mess around with what this value of c is doing, because it'll plot different things. It plots a family of curves. But of course, we might want to do this analytically. So if we did that, we could start from the fact that if it's an equipotential, we know that everywhere on this curve, x squared plus 4y squared is the same value, c. And this looks conic-like, or it kind of looks like a circle equation with these x squareds and y squareds. We usually like to analyze this when it's equal to 1. So we could write this as x squared divided by c plus 4y squared divided by c is equal to 1. And here's actually where I would stop. If you're a conic enjoyer, you could manipulate this even more and find some axis lengths and things. But we have something squared plus something else squared equals 1. And that is the form of an ellipse. And as a bonus task, I guess, you could figure out what the length of the minor and major axes are for this ellipse by sending this guy to the denominator. You'd get like a square root c and a square root c over 2, I think. On the figure below, draw the equipotential curve containing the point 0, comma a, and draw the direction of the E field at that point. So first of all, 0, comma a, that's right here. So we're looking at all points that satisfy x squared plus 4y squared equals c. And we're given that 0, comma a is on this curve. So 0 squared plus 4a squared equals c. So this means that c is 4a squared. So we could go ahead and now use that to work out kind of some other points on this curve. Like we know it's going to be some sort of ellipse centered at the origin. So it's just a matter of figuring out exactly what these lengths are. So by symmetry, we know this is also going to be a point, and we can check that the x equals plus or minus 2a is also on this. You could kind of just reason that based on how this is stretched, but of course we can prove it, because if we try to plug in like 2a comma 0, we'd get 2a squared plus 0 squared equals c. So 4a squared equals c. So this means that the point 2a comma 0 is on the 4a squared equipotential, which is the one we've been graphing. So we can do our best ellipse here, and I can actually cheat a little bit and see if I can somehow make an ellipse. Yeah, we'll take that. Of course, I'm cheating and using tools, but look at that. There's my nice little equipotential curve. So this corresponds to the potential being stuck at a value of 4a squared. And also we want the E field at this point. Well, we know that v equals 0 at the origin. And based on the symmetry of this setup and the fact that we proved last time that the E field is always perpendicular to these equipotential curves, we know that E field points either this way directly up, or this way, directly down. And it's actually this point directly down because we know that the origin is our lowest potential point. Because if we actually look at a 3D graph of this, we see that this bottom point is a sort of valley and it expands out from there. All right, derive an expression for each of the following: the horizontal component of the field at B comma B, the vertical component of the field at B comma B, and the net field. So horizontally, we just use the horizontal slope. So here is where you could use the Calc 3 idea that the electric field is the negative of the gradient of the potential. But we're just going to break it down. So what we're doing here is just breaking down this gradient into two parts. So horizontally, our horizontal E field is just the slope of V in the X direction. If I can actually draw. I use the curly D to show there's different things happening, but you could totally do the regular one. I switch up because AP, you really don't need the partial symbol. But this is the negative derivative with respect to x of x squared plus 4y squared. And these are x and y, and we just want the x derivative. So the only thing that is affecting this derivative is the x term, because this 4y squared has no x in it. So this is going to be negative 2x in the I hat direction. And we want the field at x equals b. So at x equals b, we know that my magnitude of the E field is just going to be 2b. Now, we're going to save ourselves a whole lot of time here. Do a little copy paste. And now we're just going to change a couple things. So we want the vertical component. So instead of x, I want y. So I'm going to change all of these things. And we can save ourselves a lot of time here. So I want the y component of the field. So I'm taking the y downhill slope. And in this case, it's not the x that gets differentiated, it's the y. So I ignore the first term. And what's the derivative of 4y squared? Well, it's just 8y. So at y equals b, we get 8b. And what's the net field? Well, we just said the horizontal field was 2b in some direction. And the vertical field was 8b in some direction. You know what? Actually, let's make this upwards just for consistency, because this is either going to point directly towards or directly away from the origin. And we know this is a right triangle. So, of course, to get our resultant E field, what else but Pythagoras? So we know that our magnitude of the net E field is going to have a unit of b. So we know it has a unit of b, and then under the square root, we have a 2 squared and an 8 squared. So we can Pythagoras that. We get square root of 4 plus 64 times b. And we get square root of 68 times b. One number off greatness under that square root in either direction. 68 is our forgotten number, overshadowed by its older and younger siblings. All right, negative charge placed at 0, a, and it's moved to 0, 5a, indicate whether the potential energy increases, decreases, or remains constant. Justify your answer. So we know that 0, a, that was actually given to us that 0 comma A was this like top of the ellipse. And we know that the E field pointed down at that point. So if I take if I take a negative charge and I move it somewhere up here, we're asking how that changes the potential energy of the particle. And I shouldn't say this. I should say the particle field system. I don't know how that made it through. But again, we can just say that, well, we're going to move against the E field. And if you move against the E field, that means you move uphill. So delta V is going to increase. So V increases, which means that delta V is a positive number. Because if moving with the field takes you downhill, moving against the field has to move you uphill. And then from there, we just use the fact that delta U is Q delta V. So if Q is negative and V is positive, this means that delta U is going to be negative. So U decreases. Let's run through that argument again. So this does count as qualitative because we did not actually go through and plug in all our values to the potentials to deal with this. So we said that we're moving against the E field. And if you move against the E field, that's traveling uphill, so it's a positive potential difference. And change in energy is that potential difference times your charge. So we said this was a negative value and this was a positive value. So we end up getting a negative value out for our potential energy change. So U decreases of the system. All right, now we will do a classic problem two ways. So this is the electric field strength due to 2-point charges that are along the y-axis or x-axis. We want the field along the y-axis though. So we have this sort of symmetry problem. So first we're going to just redo this old electrostatics problem. So again, how we did this before is we utilized a lot of symmetry. So we're going to use our sources and sinks rule for this. So both of these Q's are going to be sources, because a positive charge would get directly repelled by each of these. So we see that what ends up happening is we're going to have this sort of net electric field that points directly along the y-axis. So now it's just a matter of doing some trigonometry. So we know that my net electric field in this problem is going to be 2 times the y component of 1 electric field, because the x components cancel and the y's add. So my net field is just 2 y fields. And of course, if we're dealing with extracting components, that means we need to draw some sort of a right triangle and use some trig to break this triangle apart. And if you always use the polar angle, you can always make it so the polar conversion works. So I always just stick with this polar angle that we'll call theta. And I want the y component or the opposite component, so I'm going to use sine. So for some distances to fill in, this was defined to be A. This is a spot on the y-axis, y of our choosing, so the hypotenuse is just the Pythagorean distance. So what is sine theta? Well, first let's get E. E from a point charge is kq over r squared. So our r is that Pythagoras term, so I square that because we know that E is kq over r squared. And what is sine theta? Well, sine theta is opposite over hypotenuse. So the opposite side is y, and the hypotenuse is the Pythagorean term. So we get 2kqy on top. And then on bottom, we have the root term is to the 1/2 power. So the non-rooted term is to the 2/2. So we have 1/2 and 2/2, which makes 3/2. Did I ask about direction? Yeah, I guess I did. And this, we know that the field is going to be up for positive values of y. So this gets, you can tack on a little j hat. So we're actually going to show that the reason we just ask this old problem is because you might want to do it a totally different way. So the thing that makes this problem tricky is the trig and components. So we can actually avoid that entirely just by using potential. So first it says just use potentials first. So if we draw this same setup, where we said that, we'll just redraw our little triangle here, where we said this distance was y, this distance was a, this was the Pythagorean distance. The net potential is just going to be the sum of the potentials. And electric potential doesn't care about direction or anything. So it's just the sum of all the kq over r's. So I just have 2 point charges that are a distance square root y squared plus a squared away. So that gets us the electric potential. Great. Not what we wanted. We wanted the field. But now we have a way to quickly go from potential to field. Because we know that the electric field in the y direction is the downhill slope of the potential. So we can just take the y derivative of 2kq over square root a squared plus y squared. And these always look intimidating, much more in physics class than calculus because of all the constants. So let's pull out the negative and the 2kq and maybe rewrite that as a power on the bottom. So we just want negative 2kq times the derivative of, well, a root on the bottom, that's just the negative 1/2 power. So let's use the power rule and chain rule on this. So negative 2kq still lives out in front. And then the thing I differentiated, I bring down the negative 1/2 power. I decrease the power by 1. So subtracting 1 from 1/2 gets us negative 3/2. And then can't forget the chain rule. Got to multiply by the derivative of the quantity on the inside, which is 2y. And would you look at that? It all works out because, first of all, the negatives cancel. These 2's cancel. So that leaves us with a 2kqy on top and a negative 3/2 power, which can just be written as a 3/2 power on the denominator. Exactly the result we expect. So again, let's scroll up in case we forgot. 2kqy over a squared plus y squared to the 3/2. Yes, indeed. So if you get tripped up by this trig stuff and you remember potential, potential is a quick way to get to field without having to do any trigonometry. So why might a student pick the approach in B instead of A? Well, potential is a scalar. So it is easier to find the net. It is easier just to find the net potential. And if you're good at your calculus skills, you might prefer this way. If you're better with your trig and working out components, you might prefer the E field way. Yeah, it kind of just depends on the problem. Just realize you always have both ways. So the key here is that potential is a scalar, which makes the problem easier to find VNet. All right, and now just a couple wrap up questions going the other way, where we can integrate our parallel component of the E field to get the total downhill change. Because if E is the downhill, if E is the downhill slope, if you add up all the downhill slopes, you must have figured out how much downhill you traveled. Because the integral is adding up things, so we're just adding up all these downhill slopes. So that's all this is saying. It's just a reverse. So if we're given our slopes here, we want to find the potential difference as we move a particle from x0 to xf through this field that's given as follows. So we actually know if we graph this, or just like kind of visualize this on a line, what this field looks like. This is our origin right here. This is a field that gets stronger and stronger to the right as you go, as you go away from the origin. So, oh, it says the positive x-axis anyway. So we got something kind of like this as our field, where particles are getting pushed harder and harder and harder to the right as they go on. All right, so the definition of potential difference from field just says we just take the negative of the E field, and I always like not just calling it delta V. I always like saying what points we've traveled to and from. So we're moving from x0 to xf. So from x0 to xf. So I actually denote that as follows, where I go from x0 to xf. And notice this also shows up in your integral bounds. And you don't need the vector. We just need that sort of magnitude here. The dx sort of takes care of that for you, understanding that this is in the x direction. And now it's just a simple antiderivative. So we get cx cubed over 3, negative cx cubed over 3, evaluated from x0 to xf. So we can write this as negative c over 3 times the quantity xf cubed minus x0 cubed. And which point is at higher potential, x equals x0 or x equals xf? Well, we were given in the problem that c is positive and xf is a bigger number. So we actually know that delta v from x0 to xf is a negative quantity. And since this is a negative quantity, this tells us that we have gone to a lower potential. So this means that v at x0 is going to be at a higher potential than xf. Also, we could have seen this just by looking at our little field plot here, because this is the E field. So if the E field points downhill, we know that the potential is getting more and more negative as we go to the right, because the E field points towards downhill. So we know that xf is downhill of x0. All right, now for our last problem, we have actually the same graph as before. That was intentional. One, it saves me figure creation. And two, we can actually see how to interpret the same graph in different ways. So it's not totally the same graph, because last time we graphed V, this time we graphed E. So here is just the horizontal field strength along the x-axis, and we are interested in placing a proton at x equals 0 and launching it with a speed v0 to the right. And we want the speed of the proton upon reaching x equals 6d. So first of all, looking at this graph, if I place a proton with an initial velocity and sort of shoot it that way, protons accelerate with the E field, so it's going to speed up, speed up, speed up, speed up with increasing force, keep speeding up with a constant force, and eventually it's going to reach x equals 6d. So my speed should increase because it's getting pushed to the right for most of its journey. except for this tiny little piece down here. But we should get an increase in speed. So, of course, when interpreting a graph, we have to figure out what about the graph we're interested in. And our answer is we either read the graph, we read the slope, or we read the area in some capacity. We already dealt with slope, so you can probably guess what's happening next. And this is definitely a conservation of energy problem, right? Because we want speed. So we know it's related to delta K is negative delta U, which is negative Q delta V, which is negative, it's a proton, so it's going to be E times delta V. All right, and that's where we have to stop because we are not given any information about delta V. But we know how we can get it because our relationship, our field potential relationship for this problem, will utilize the fact that delta V is the sum of all of those downhill slopes. And in this problem, that's just going to be interpreted as well. That's going to be the negative of the area. Because if slopes are interpreted for the derivative, we know that that integral is interpreted as an area because it's these products, right? I'm multiplying a base and a height, so we know it's areas. Okay. So, of course, this is very geometric, so it's pretty easy to split this up into things to take the area of. So, first up, we have this triangle. So, 1/2, its base is 2, and its height 2D, and its height is 3E. So, this area is 3ED. Then for my green rectangle, I know trapezoid enjoyers are yelling at me. Yes, I know this is a trapezoid. But I find it, I like to split it because people find it easier than dealing with the trapezoid most times. You are a rectangle. You have a base of 2D and a height of 3E, so this is 6ED. Then we have a blue triangle. Sorry, I already used blue. We have a purple triangle. Base is 1, height is 3, so this is 3/2 ED. And then we actually have the same triangle down here, but we have to be careful. It is below the x-axis. So this is negative 3/2 ED. So we can go ahead and just find our net area under the curve just by adding all these figures together. So our delta V is just going to be the negative of all of these areas added together. So we have a positive 3ED because it's above the x-axis, a positive 6ED that's above the x-axis, a 3/2 ED that's above the x-axis, and a 3/2 ED that's below the x-axis. So again, with that, we could have just canceled these instantly. So as soon as you saw by symmetry these cancel, you could have just done that. But just for completeness, I kept it. And this is going to bother me. Let's fill in the side of the triangle. Okay. And now we can say our net delta V is just the negative of 3 and 6, which is just going to be 9 ED. Makes sense. We should have a negative potential difference because I'm going with the E field for almost all of my journey. So it should be a downhill. So now we can just go ahead and set up our relationship because we know that our delta K is just the opposite of Q times the delta V. So 9 EED is our delta K. That is a positive quantity, right? Showing our particle speeds up. So then we just do our 1/2 mv squared minus 1/2 mv squared equals 9 EED. We can multiply everybody by 2. And to get mvf squared minus mvo squared equals 18 EED. Divide everybody by m, we get vf squared minus v0 squared equals 18 EED over m. So then we just add VO squared to both sides, take a square root, and we get VF is just the square root of VO squared plus 18 EED over M. And that's our answer. notice it is definitely a larger speed than v0 as expected. So that's all the calculus relationships. So that's how we relate all these with calculus. And now that means our next part is going to be expanding from just point charges to just shapes with charges inside them.